Hello students, I am Dr. Premlata Verma from Government Bilasa Girls PG College, Bilaspur, and today I am going to deliver a lecture for M.Sc 4th semester mathematics class, and paper is fuzzy sets and their applications. Topic of today's lecture is approximate reasoning. Today is my third lecture on approximate reasoning. Today we are going to cover reasonable axioms of fuzzy implications with some theorems. Before we write the reasonable axioms of fuzzy implications, let us first learn this terminology. If A is less than or equal to B, then A is called antecedent and B is called consequent. So, with this thing in mind, let us proceed to define the reasonable axioms of fuzzy implications. First, there are 9 reasonable axioms of fuzzy implications. Let us first see in brief what are the 9 axioms. Axiom 1 is monotonicity in first argument. Then axiom 2, monotonicity in second argument. Then axiom 3, dominance of falsity. Then axiom 4, neutrality of truth. Axiom 5, identity. Then axiom 6, exchange property. Axiom 7, boundary condition. Axiom 8, contraposition. And axiom 9, continuity. Now let us see the axioms one by one in detail. What is axiom 1? Monotonicity in first argument. A is less than or equal to B implies IAX is greater than or equal to IPX. Since we are defining the monotonicity in first argument, therefore this X will be placed in the second argument. That means that the truth value of fuzzy implication increases. This is greater than or equal to, so this increases as the truth value of the antecedent decreases. This increases, this decreases. So this is monotonicity in first argument. Then axiom 2, monotonicity in second argument. This is written as A is less than or equal to B implies IXA is less than or equal to IXB. Here X is placed in the first argument. And this is monotonicity in second argument. So this means that the truth value of fuzzy implication increases as the truth value of the consequent increases. This is consequent. So truth value of fuzzy implication increases as the truth value of the consequent increases. This increases, consequent increases. Axiom 3, dominance of falsity. I0A is equal to 1. This means that falsity implies everything. This is the interpretation of axiom 3. Axiom 4, neutrality of truth. I1B is equal to B. This means that the truth value does not imply anything. In falsity, we have to write 0. In neutrality, we have to write 1. This means that the truth value does not imply anything. Now come to axiom 5, identity. IAA is equal to 1. That means first argument and second argument both are same. This means that the fuzzy implication are true. True means 1. Whenever the truth values of the antecedent and consequent are equal. Now come to axiom 6, exchange property. We see that there are 2 symbols of I. Here also there are 2 symbols of I. And what is the difference between the left and right? Here A and B are in this order, and here the order is BA. So this is a generalization of the equivalence of A implies within bracket B implies X and B implies within bracket A implies X that holds for the classical implication. So this is exchange property. Boundary condition. IAB is equal to 1. If and only if A is less than or equal to B. That means whenever the first argument is less than or equal to the second argument, then implication is equal to 1. This means that fuzzy implication are true if and only if the consequent is at least as true as the antecedent. Now come to axiom 8. This is contraposition. IAB is equal to ICB-CA. Here there is A and B, and as soon as we write C, the role gets reversed, CB and CA. So IAB is equal to ICB-CA for a fuzzy complement. This means that fuzzy implications are equally true when the antecedent and consequent are exchanged and negated. These are exchanged and negated. Negated means complement. Now, continuity. Axiom 9. I is a continuous function. This property ensures that small exchanges in the truth values of the antecedent or consequent do not produce large changes in truth values of fuzzy implications. Otherwise, there is discontinuity. So, small changes in the antecedent or consequent do not produce changes in truth values of fuzzy implications. So, students, there are 9 axioms. It should be borne in mind that axiom 3 and 4 can be derived. Axiom 3 and 4, dominance of falsity and neutrality, 3 and 5, the axioms 3 and 5 can be derived from axiom 7, dominance of falsity and identity. These can be derived from axiom 7, but even then we write the axioms 3 and 5. The reason is that there are many implications which do not satisfy axiom 7, but they satisfy axioms 3 and 5. So we have a big list of examples of implications in which it has been mentioned that a particular implication satisfies what number of axioms. So let us see the list. The list is, see here. There are many types of implications. Their symbol is written like this. You are not required to learn these symbols. All symbols are not to be learned. And the class, that is R implication, S implication, QL implication. So this Zade, this is a QL implication. The function is defined like this, and this satisfies these 5 axioms. The complement is standard complement, and the year when it was defined is written in this. This is a copy of from book of Clear. Then Guinness riches, this Gödel. So in our theorem, in our next theorem, we must learn Gödel, Gauguin, and WU implication. This Gödel is an R implication, Gauguin as an R implication, and this WU, the type of implication is not mentioned here, but it is defined. So first we will see what is Gödel implication. It is a type of R implication which is defined as IAB is equal to 1 if A is less than or equal to B, B if A is greater than B, and this satisfies the axioms 1 to 7. Then Gauguin, this implication IAB, this is an R implication. It is defined as IAB is equal to 1 if A is less than or equal to B, B by A if A is greater than B, and it satisfies 1 to C axiom and 9th axiom. It does not satisfy 8th axiom. And then come to WU implication. It is defined as IAB is equal to 1 if A is less than or equal to B, then minimum 1 minus A, B if A is greater than B. So for the next theorem, you make a table for Gödel, Gauguin, and WU implications so that at a glance you can learn the 3 types of implications that will be useful for you, because from this whole list it is not easy to memorize the 3 implications which are to be used in the next theorem. So students, you write on your copy only these 3 implications. Now we come to theorem 11.5 of the book of Clear. The statement is, let the range of the membership function A is by is equal to supremum x belonging to x I ax comma implication I within bracket ax comma by covers the whole interval 0, 1. Then the following fuzzy implications satisfy 1 for any T norm. The 3 types of implications: Gani's-Riches, Gödel, and W. We had seen here Gani's-Riches, Gödel, and W implications. So these implications should be learned before proving this theorem. So what we have to do is that we have to prove that this Gani's-Riches implication satisfies this equation 1. Gödel implication also satisfies this equation 1, and W implication also satisfies equation 1. So what is Gani's-Riches implication? This is ISAB is equal to 1 if A is less than or equal to B, and 0 if A is greater than B. Here it is written. So then what we are going to do is that we have to prove this expression, equation 1. We will start from the right hand side. We are writing supremum x belonging to x I ax comma is. Is, it is a symbol for Gani's-Riches implication, is ax by. We are putting A instead of ax. So when we had written x belonging to x, that will be replaced by A belonging to 0. So ax is A. Here also substitute A instead of ax. So this is equal to supremum A belonging to 0, 1 I A is within bracket A by bracket closed. So we know that here how this next expression has come. We know that if we have a set of 100 natural numbers which are selected from the set of natural numbers at random, and sequence is not also proper. So if we have 100 natural numbers randomly written and we have to find the supremum of that set, then we can also break that set of 100 elements into 2 parts. First set consisting of 20 elements suppose, and the second set consisting of 80 elements suppose. Then we find the maximum of first set, then we find maximum of second set, and then we take the maximum of the 2 maximum elements obtained from the 2 sets. Then that maximum will be equal to the maximum or supremum of the set of 100 natural numbers. That is the idea behind this step. So supremum x belonging to x, ax, this is written as like this, A belonging to 0, 1 I A is by. So we are breaking this in 2 parts. One, A belongs to 0, 1 is written. So we will take all those A which are less than or equal to by, and we will take all those sets which are greater than by. So all the elements of 0, 1 will be covered, A less than or equal to by and A greater than by. So maximum, so we are breaking this into two sets. So maximum one set is this one and the other set is this one. So here supremum A is less than or equal to by and A greater than by. Now this is equal to maximum. A is we have to take the supremum when A is less than or equal to by. So what we will get here? ISABY. This will be equal to what? 1. So supremum A belonging to by. This A is copied from above and the supremum we have to take here. So this will be what? ISABY. This has been defined like this. So from this definition we get ISABY as 1. Okay. Then supremum A greater than by. ISABY. ISAB, this is defined as 0, A greater than B. So we are writing 0 instead of this. This has come from this definition of Keynes-Riches implication. So we got like this. Now this is equal to maximum. Now what will be the supremum here? What will be the supremum? The supremum will be A. And what will be the supremum here? The supremum will be 0. So because IA1 is equal to A and IA0 is equal to 0. So this has come from the axiom of T norms. IA1 is equal to A and IA0 is equal to 0. So maximum, supremum A less than or equal to by and supremum 0, A greater than or equal to by. So this becomes maximum supremum A and here this will come to be 0. So this is equal to maximum supremum A less than or equal to by was there. So this will become by and this is 0. In the next implication, so we have proved next line is equal to by. Here you have to write by. So what we got? This line, that is, this is the left side, right side of this expression is equal to, this answer will be by. So this is proved that Keynes-Riches implication satisfies equation 1. Now we will prove Gödel implication satisfies expression 1. So Gödel implication IG. IG is defined as IGAB is equal to 1, B, A less than or equal to B, A greater than B. Here also we have to do the same thing. That means we have to break the set in two parts. Supremum X belonging to X, IAX, that means right side of the expression 1. We have to write and start AX is equal to A. So supremum A belonging to 0, 1, IAIG, ABY. This is equal to maximum of these two sets, A less than or equal to BY and A greater than BY. This expression, these two sets, these two type of expression are written for all the three implications. So maximum like this. Only definition of the implication changes. Steps are same. So maximum supremum A is less than or equal to by. This IA1, because we have from here for A less than or equal to B, IAB is equal to 1. Same thing, that A is less than or equal to by. A is less than or equal to by, so value will be 1. So we have written 1 in place of this. Similarly, IGABY, A greater than by. For A greater than B, we get B. That means here we will get what? by from this. So maximum supremum A is less than or equal to by. From the axioms of T norms, IA1 is A and IABY is by for A greater than by. So because it is written that by is minimum. Here minimum. A and by, this smaller one is by. So this is equal to maximum. This will come to be supremum of all those A which are less than or equal to By. So the supremum answer will be By, and this is again By. The maximum of By and By will be By. So the right hand of the expression of equation 1 becomes equal to By. That means this Gödel implication satisfies equation 1. Similarly, WU implication, IWAB is equal to 1, minimum 1 minus AB, A less than or equal to B, A greater than B. Then again the right side, supremum I, AX, IW, AX, BY. This is equal to supremum. We write A instead of AX, supremum A belonging to 0, 1, I, A, IW, ABY. This is equal to, we break in two parts, maximum, supremum A less than or equal to BY, I, A, IW, ABY, and supremum A greater than By, IA, IW, ABY. Now we write the value of this and this with these two conditions from this definition of WU implication. So we get maximum, supremum A less than or equal to By, IA1, and supremum A greater than By, IA, minimum 1 minus A, By. Then we get maximum, supremum, this from axioms of T norms, IA1 is equal to A, and here IA minimum 1 minus A By. So here minimum is By. So we write here By because A is greater than By. So this is A By. What we get, maximum By here, and from here minimum is By. So this is By, this is By. So the equation 1 is again satisfied by WU implication. Now we come to theorem 11.8. Theorem 11.8 from the book of 12. What is theorem 11.8? Let us come to the statement. Let IAB is equal to maximum 0 A plus B minus 1 for all A and B belonging to the closed interval 0, 1. And let IA be the Lucas-Lewis implication. This L, since it is the name of a mathematician, it should be written in capital letter. So correct this word, students, and let IA be the Lucas-Lewis implication, that is omega IAB is equal to IAAB, and Lucas-Lewis implication, even if it is not given in the question, you must remember Lucas-Lewis implication. It is not necessary that the examiner gives you the definition of Lucas-Lewis implication, even though it is written in the theorem. So you must remember the Lucas-Lewis implication. So what is omega IAB is equal to IAAB is equal to minimum 1 minus A plus B for all A and B belonging to 0, 1. Then we have to prove that AO omega IP is equal to CBO omega ICA whole inverse. This omega I, this is infimum omega I composition we have learnt in chapter 5 also. So we have to prove this expression. This holds for any fuzzy sets A and B, and consequently R cap is equal to A omega IB is the greatest approximate solution to B is equal to A OIR. This is SUPI composition, and CA is equal to CB SUPI composition R inverse. So what we have to do is we have to prove this expression denoted by equation 1. And for the standard fuzzy complement, this is also mentioned. So let us start the theorem. We will find the value of this left hand side expression, and then we will find the value of the second right side expression, and we will see that both the sides are equal, and then this equation will be proved. So let us start with the left hand side. So for let x belongs to x and y belong to y, then a omega I b xy, this is equal to omega I ax by. And this omega I ax by, this has been defined as omega I ab is equal to minimum 1 minus a plus b. So instead of a, we have to write ax, and instead of b, we will write by. So from this we get minimum 1 minus ax plus by. So this is the value of the left hand side expression of equation 1. Now we start with the right hand side of expression 1. That is CB infimum omega I composition CA whole inverse XY is equal to, as we know that whenever R inverse XY, when we say R about the fuzzy relation, what we write? R inverse XY is equal to RYX. Same is the condition here. In order that minus 1 is not written, then what we will do that CB omega I CA inverse XY, this is equal to without inverse this expression, and this ordered pair elements will be interchanged. So R inverse XY is equal to RYX type of expression. So this is equal to omega I CBY CAX. From where it has come? Here. A omega I BXY is equal to omega I AX BY. So CBO omega I CAYX. Then what we will do? Instead of A, we will write CB. Instead of B, we will write CA. And instead of X and Y, we will write YX. So what we will get? Omega I AX. Instead of AX, what we will write? C, this is C by and C AX. This is omega I C by C AX. Okay, this has come from this. This is equal to omega I C by standard complement 1 minus by and standard complement 1 minus AX. So this is equal to minimum. This has come from the expression here. This is equal to minimum 1 minus AX plus by. So instead of, so what we are going to do, that instead of this omega I 1 minus by, instead of AX we are going to put 1 minus by, and instead of by we are going to put 1 minus AX in this expression. So we will get minimum 1 minus by plus 1 minus AX. This is equal to minimum 1 minus AX plus by. 1 and 1 will cancel, and we see that this is the left hand side of it. The expression 1, minimum 1 minus AX plus by, and right hand side is also minimum 1 minus AX plus by. So the expression 1 holds. So students, this is the proof of this theorem, and this is the end of today's lecture. Hope you will do well and you will find this lecture fruitful, and all the best for your exam. Thank you very much.